Okay, so this is our lesson on vectors. And vectors are used to represent quantities that have both magnitude and direction. So, for example, if we think about the difference between velocity and speed, so if I said I was driving 70 miles per hour, at a speed of 70 miles per hour, that would represent a speed, which speed only has a magnitude. However, if I were to say that I was driving 70 miles per hour north, where I include a direction, that would end up representing a velocity. Velocity has both magnitude and direction, and velocity is a vector quantity. So vectors have both magnitude and direction, and are used to denote quantities such as velocity as well as force. So velocity is speed in a certain direction, and force is weight in a certain direction. So up until now, you guys have been talking about different scalar quantities. And scalars are basically just real numbers that are used to represent magnitudes like speed or mass or time. But they don't have any sort of direction. Anytime we want to represent a quantity that has both magnitude and direction, we have to think vectors. So vectors can be represented geometrically with a directed line segment. Here are some of the common notations for vectors. So in different text, you may see like lowercase letters in bold will be used to represent a vector or name a vector, or the lowercase italicized letter with the arrow over the top. U and V are very common vector names. And then there's also this notation where you have like the initial point of the vector and the terminating point of the vector to represent. So like if A were the initial point and B were the terminating point, and then the arrow over the top, that can also be used. So if this were vector U, you can also think of the initial point as being known as the tail of the vector, and then the terminal point as the head, or even as the tip of the vector. So in this class, we're going to limit vectors to be in a plane in 2 dimensions. However, vectors can be represented in 3 dimensions geometrically and algebraically, and then you can also represent vectors in higher dimensions algebraically. You can't draw something or visually represent something in 4 dimensions, but we can think about in higher dimensions representing those vectors algebraically. So for what we can think about geometrically, 2 dimensions and 3 dimensions, I'm just going to draw a little picture here. So in 2 dimensions, in the XY plane, we can think about having a vector. Let's say that the initial point is at the origin, and then it terminates at some point x comma y. Okay, so that would be a vector in 2 dimensions. And we could also think about moving that vector around the two-dimensional plane. So this is in 2 dimensions. And then if we were to add a 3rd dimension, so think about adding 2 dimensions represents a plane, and then thinking about adding a 3rd vertical dimension. So to draw this, I'm going to do the best that I can, but it's difficult to draw 3 dimensions on 2 dimensions. So let's say that this is the XY plane. I'm just kind of making it so that it looks like it's kind of angled here. So the X and the Y axis, these extend in all directions. Then let's think about having this 3rd axis coming up through the origin, and we can call that the Z axis. So if we have a vector in 3 dimensions, we're thinking of that vector as not necessarily being on the XY plane, although it could be, but coming out where somewhere in 3-dimensional space, and we could call that point where it terminates the point x comma y comma z. But that vector could also move about three-dimensional space, not changing its magnitude or direction, but we could think about it moving around, just like we would in 2 dimensions. So this was my 3D picture, my attempt at a 3D picture. So we're going to look first at the geometric interpretations of vectors. So what the magnitude, direction, what equal vectors look like, what vector addition, also including subtraction, looks like from a geometric perspective. And then we're going to actually talk about algebra with vectors. So the magnitude of a vector is just the length of the vector, the length of the directed line segment that represents the vector. Magnitude, another term for magnitude is norm, and there's 2 different notations that are commonly used to represent magnitude. So just the absolute value bars, but also like these double absolute value bars can be used. So if we have a vector, which I'll name u, so let's say this is the vector u. The length of u from tail to tip or tail to head would represent the magnitude of u, or the norm of u. So we haven't talked about how to calculate that length yet, right? It starts at a point, then ends wherever that arrow stops. We haven't talked about how to actually calculate the magnitude of a vector, but that's geometrically the magnitude of the vector is the length of the directed line segment that represents the vector. Now, 2 vectors are considered to be pointing in the same direction, or 2 vectors have the same direction if they're parallel to each other. So if we were to draw 2 vectors in the xy plane, they don't have to have the same magnitude, so they can be different lengths. So let's say we have this vector, which I'll call u, and then this vector v. Okay, I'm doing my best to make those vectors look like they're parallel to each other. They have different magnitudes, but they're parallel to each other. These vectors would have the same direction if they're parallel, but also if we were to move them to both have their initial point at the origin, they should overlap. And their direction could then potentially be described by this angle theta. Now we can move vectors about the xy plane. So like we can also think about like these 2 vectors can still have the same direction, where if this angle, so the angle from horizontal, if that angle is the same, then the 2 vectors would be parallel. They would be said to have the same direction. 2 vectors are pointing in the opposite direction if they're parallel to each other, but the arrows are pointing in the opposite direction. So meaning an interpretation of that in the xy plane would be, let me see. So let's say we have one vector, how about I'll call this vector W, and another vector which should look parallel, is maybe shorter. I'll call this one vector, how about vector Z? Okay, so these vectors should be parallel, but they're pointing in opposite directions, meaning if we were to move each of the vectors so that the initial side of the vector were touching, the the origin, the angle between the two vectors should be 180 degrees, right? This angle should be 180 degrees, or pi radians. They're parallel, just pointing in opposite directions. Arrows are on opposite sides of the directed line segment. Okay, this should be kind of obvious, but two vectors are considered to be equal vectors if they have both the same magnitude as well as the same direction. So you can have two equal vectors in the xy plane, and they'll be considered equal if they have both the same magnitude and direction. So like, let's say this is one vector. I'll call this vector u. And then if I copy and paste this somewhere else, and maybe I'll change the color and then call this vector v. Okay, so these vectors would be considered to be equal vectors as long as their magnitudes, so their lengths, which we know they would be the same because I just copied and pasted. So if their magnitudes are equal to each other, and they also have the same direction, meaning this angle would be the same. So if you were to move them both into the position of them having their initial point on the origin, they would just end up completely overlapping each other. So we're going to talk about the geometric interpretation of vector addition, and there's two different kind of perspectives or methods that we think about when we think about vector addition. So there's the first one that we're going to look at is the tail to tip method, and that would be thinking about having two vectors. So let's say that we have like vector u and vector v, and the tail to tip method would be if we wanted to find the vector that we would get from adding vector u plus vector v. So vector u plus vector v is what I'm going to name this new vector that we get from adding the two vectors together. And this is the geometric interpretation. We're also going to talk about the algebraic interpretation, which is pretty straightforward, but I want you to understand the geometric interpretation. So if we were to copy vector v and do exactly what the method's called, we're putting the tail of vector v to the tip or the head of vector u. The resultant vector, the vector that we get from adding the two vectors together, would be going from the tail of u to the tip of v. So this vector here would represent the vector u plus v. I could name it something different, like I could call that vector w, but that vector w would be the result of adding vector u and vector v together. So this is what we call the resultant vector. The resultant vector is what we get from adding two vectors together. Okay, the other method that we can use to think about the geometric interpretation of adding two vectors together is the parallelogram method. So if I were to take those same vectors, let me just copy and paste these, Copy. Okay, and I'm going to think about putting the tails of the two vectors together. You move the name of vector v here. If we were to think about drawing a parallelogram, constructing a parallelogram, so thinking about the side that would be parallel to the vector v, so same length and direction. I could also think about copying and pasting vector v. And then getting the side that would be parallel to vector u. The resultant vector would be this diagonal. So this would represent the vector u plus v. Okay, and you can see that how they would be the same. Like if we went back up here and we thought about drawing a parallelogram, right? Like if we thought about this being vector u, angle slightly off. So if we thought about this being vector u, this being the parallel side to vector, or sorry, the orange being parallel to vector v, and then the side being parallel to vector u, we would create a parallelogram where the resultant vector is that diagonal. Okay, so those are the two geometric interpretations of vector addition. When we add two vectors, we get a resultant vector. Now, vector subtraction is based on vector addition. So let's first think about tail to tip method for vector subtraction. Okay, so in that case, we're going to think about, here, let me use another color. Yeah, let's use blue. So we're going to think about vector u minus vector v as being vector u plus negative vector v, which negative vector v is just vector v pointing in the opposite direction. So in the picture where, let's do two, here, let's just do two, I guess we can use the same ones. Copy. Okay. So if this is vector u, tail to tip method. So if we were thinking about adding u and v together, we put them like that. But negative vector v would just be this vector let me change the color, pointing in the opposite direction. So pointing in this direction. This vector right here would be negative vector v. So thinking tail to tip method, that means u plus negative v would be this vector right here. So we can call that blue vector, vector u minus vector v. And then for parallelogram method, okay, so I'm going to copy and paste vector u and vector v again. Okay. So if we just thought about constructing the parallelogram from adding vector u and vector v together. Oh, sorry, we would put those the two tails together. And then constructing a parallelogram to the same picture that we drew above. Now, this ended up being the resultant vector from adding u and v together. Subtracting ends up being the other diagonal. So this would end up being the vector u minus vector v. Okay, and you can see kind of from the tail to tip method that those end up being the same. Okay, so geometric interpretation of vector addition and subtraction. So now we're going to move on to talking about the algebraic interpretations of vectors. So a position vector, so we can move vectors around the xy plane, around 2 dimensions. A position vector is a vector whose initial point is at the origin. We refer to this as a vector that is in standard position. So vectors in standard position, I'm going to draw a picture, just a vector in quadrant 1, but the vector in standard position can terminate in any of the quadrants. So if this is our vector in quadrant 1, we can say that the vector terminates, it starts at 0, 0, the origin, and then it terminates at some point a comma b, right, x comma y. And we can represent this vector, which I'll name vector v, as a horizontal and vertical component. So the horizontal component will be A, the vertical component will be B. So it's basically A comma B indicates where the vector terminates, the terminating point of the vector. These pointy brackets tell us that the vector is in standard position. So when you see a vector with horizontal and vertical components represented in the pointy brackets, that means that the vector is in standard position. We call A the horizontal component. And we call B the vertical component of the vector. This is also in some texts referred to as component form. And it just represents a vector that is in standard position. Some other notations that represent vectors that are in standard position, but we're not going to use this first one, but we can represent vectors in standard position in as a column matrix. This may come up at the BC level or maybe linear algebra. So like a college level math course. And then there's I and J form, which we are going to talk about. Okay, so these are a couple other forms, but typically we're going to be representing vectors that are in standard position in this form, component form, with the pointy brackets. Okay, so let's do an example of finding the horizontal and vertical components of a vector that would be in standard position. So what is a vector in standard position that is equal to the vector with the initial point at 4, 5 and a terminal point at 7, 12? So it may help at first to sketch a picture of this. So the initial point is at 4, 5. So let's say 4, 5, and then the terminating point is at 7, 12. So the initial point and then the terminal point. So the arrow would be at the terminal point. Okay. So if we were to think about picking this vector up and putting its initial point at the origin, that would be the vector in standard position. And we would want to know what that terminating point would be. We could do this algebraically by thinking about how we would get the initial point to the origin. Since the initial point is 4, 5, we would need to subtract 4 units from the x coordinate of the terminating point. And then we would want to subtract 5 units from the y coordinate of the terminating point and from the initial point to get it to be at the origin. So we could say that if we call this vector v, so vector v would be equal to, we're going to use the pointy brackets to indicate that we're representing a vector in standard position. So we would subtract 4 from the x coordinate of the terminating point, and then we would subtract 5 from the y coordinate of the terminating point. And that would be 3, 7. So this would be the vector that would be in standard position and has the same magnitude and direction as the original vector. So it would be the vector that if we moved it so that the initial point was at the origin, it would then terminate at the point 3, 7. Okay, so next we're going to talk about the algebraic definition of magnitude. So we talked before about magnitude represented the length of the directed line segment that represents the vector. So now we're going to talk about how to actually calculate the magnitude, which is also known as the norm of a vector, which is easy for a vector that's in standard position. If a vector is not in standard position, you can either think about putting it in standard position, so where the initial point lies at the origin, or like if we think about the example from above, you can use just distance formula. So like the example that's above, where the initial point was 4, 5 and the terminating point was 7, 12. right? So this point being 4, 5, this point being 7, 12. You can just think about using distance formula. So the magnitude, if this is vector v, the magnitude of vector v would be the square root of 7 minus 4 squared plus 12 minus 5 squared. So that would end up being equal to the square root of 58. This is just distance formula. If the vector is in standard position, though, so I'm just going to copy and paste this. So if the vector is in standard position, right, where that initial point is at the origin, okay, and the terminating point is at, I guess I should get rid of these. My sketch wasn't super accurate. So we had determined that the terminating point would be 3, 7. Well, a vector in standard position, you could think about making a right triangle here, where this side would be a length of 3, this side would be a length of 7, and then the length of the vector, or the magnitude of the vector, would be the hypotenuse of that triangle. So we could just use the magnitude of v would be the square root of 3 squared, right? This is going off of Pythagorean theorem. So this is for the vector that's in standard position. And if we thought about using Pythagorean theorem, the magnitude of v squared would be equal to 3 squared plus 7 squared. So the magnitude of the vector v would be the square root of 3 squared plus 7 squared, so 9 plus 49, which is the square root of 58. So if the vector is in standard position, you can just think about using this formula, which you guys are familiar with, Pythagorean theorem. Or you could think about if the vector is not in standard position and you don't want to think about what those horizontal and vertical components would be for standard position, just using distance formula. So let's find the magnitude of the vector that terminates at the point -1, 5 and is in standard position. So it starts at the origin. So the magnitude of this vector, which is named vector v, would be the square root of -1 squared plus 5 squared. So that's the square root of 26, which does not simplify. So that would be the length of this vector. Okay, so let's talk direction of a vector. So the direction angle of a vector is the positive angle between this should specify the positive x-axis and a position vector. So a vector that's in standard position. So it's the angle that's in standard position. So like angles we think of as starting on the positive x-axis and then rotating in the counterclockwise direction. That's what we think of as being the direction angle. So we can use the fact that, so if we think about having a vector in standard position, to make this first example simple, I'm going to think about it being just a vector in quadrant 1. Okay, so like let's say that this is vector u in standard position, represented as A comma B, the pointy brackets. This would be the direction angle theta, and the relationship between the horizontal and vertical components and theta can be described using tangent, right? Tangent of theta would be equal to B over A. So if we took the inverse tan or the arctan of that ratio, we would get a value, we would get an angle, right, that would lie in the range of inverse tan, right? The range of inverse tan being from negative pi over 2 to pi over 2, or negative 90 degrees to 90 degrees. So inverse tan of B over A doesn't necessarily represent the direction angle of the vector unless it's a vector that terminates in quadrant 1, right? Because if B over A is positive, that means that inverse tan of B over A will represent a positive angle from quadrant 1. If B over A is less than 0, then inverse tan of B over A will be a negative angle. From quadrant 2. Or sorry, not quadrant 2, quadrant 4. So I like to call inverse tan of B over A theta star. It's not very technical, but I like to call it theta star. So I figure out inverse tan of B over A. I think about what that angle represents. And then if the vector in standard position terminates in another quadrant, I decide what I need to do to inverse tan of B over A. So let's look at an actual example here. And this is a vector that does not lie in quadrant 1. It's a vector that actually lies in quadrant 4. All right, so 3, negative 4. Okay, so this is vector U. This is the angle that we're trying to find, theta. However, inverse tan of negative 4/3 is going to represent this negative angle here. So that's why I call inverse tan of B over A, I think of it as like the possible angle, the initial angle, and then I need to figure out what the angle theta actually is. So theta is actually coterminal with theta star in this case. So we can find the exact value of the actual angle by adding 2 pi or adding 360 degrees to the inverse tan of that negative ratio. I'm going to think about adding 360 degrees. A lot of times with vectors, we're using angles in degrees, just so we can kind of wrap our brains around it better. So that would be the exact value of the angle, and then if you type that into your calculator, you get approximately 306.870 degrees. So that would be the approximation of the direction angle. and the exact value. Okay, so we talked about two vectors geometrically. We know two vectors are equal if they have both the same direction and the same magnitude. We said they would completely overlap if we were to move the vectors to be in standard position. But this is pretty straightforward. Two vectors where you know that they're in standard, so two position vectors, u and v, are going to be equal vectors if their horizontal components are the same and their vertical components are the same. So pretty straightforward. Okay, vector addition is actually really simple. You just think about adding the two horizontal components and adding the two vertical components. I want to show you why this works geometrically. So if we thought about adding vector u and vector v together, so let's think about using the tail to tip method. So let's say that this represents vector u and this represents vector v. Okay. And then the resultant vector, you guys know geometrically, would be this. This would be the vector u plus vector v. And vector u plus vector v would have a plus c as a horizontal component and b plus d as a vertical component. Well, that works out because if we thought about vector u being in standard position, horizontal component is A, vertical component is B, and then vector v has horizontal component C and vertical component D. Notice that this would be C. This would be a length of B. So the horizontal component would be A plus C, sorry, not B, C. And the vertical component would be B plus D. So it's oftentimes if two vectors are not given as position vectors, so vectors in standard form, it may be helpful to put them into standard form in order to add them together or subtract them. So let's just practice finding the vector u plus vector v, adding the components together. So vector u plus vector v would be equal to 1 plus -5 and comma 2 plus -4. Okay, so that would be the resultant vector. We can think about multiplying vectors by scalars, so performing scalar multiplication. So if k is a scalar, so basically a constant, just a real number, and you're multiplying a vector by that constant, you can just think about multiplying the horizontal component and the vertical component each by that scalar, by that constant. If the absolute value of k is greater than 1, then that means that, so its distance from 0 is greater than 1. That means it's going to increase the length of the vector. If the absolute value of k is less than 1, so like 1/2, -1/2, and you're multiplying the vector by that value, it's going to decrease the length of the vector. And if you multiply the vector by a negative scalar, so a value less than 0, then it's going to change the direction of the vector. Okay, 0 vector. I should have an arrow over the top here. 0 vector is a vector that you could think of as pointing in any direction, but has a magnitude equal to 0. Really just a point. But we have to think about vectors in order for us to have certain algebraic properties of vectors. So these are the algebraic properties of vectors. So similar to the properties of real numbers, vectors have a commutative property, like vector u plus vector v is equal to vector v plus vector u. So this is the commutative property of addition, okay? There's also an associative property of addition. Okay, we have an associative property of multiplication, but it has to do whenever we're multiplying vectors by constants. Notice we have not talked about multiplying vectors yet. Okay, we also have a distributive property. So this is, if you're adding two vectors together, you can think about distributing a constant or a scalar. Okay, and then this is also distributive property, where if you have a sum of two scalars and you think about distributing the vector. Okay, 0, or you can think of that as 0, yeah, just 0 actually, it's like a scalar 0. So 0 times a vector equals to 0, so that's 0 factor law. One times a vector is the identity property of multiplication. Okay. This just changes the direction when you multiply by -1. I don't have a name for that property. And if you were to add a vector that is pointing in the opposite direction, two vectors together that are pointing in opposite direction, they'll equal to a 0 vector. So that's the additive. This would equal to a 0 vector. So that would be the additive inverse property. Okay, so we've already kind of talked about the horizontal and vertical components of a vector that's in standard position, right? This vector means that the vector starts at the origin and then terminates somewhere in the xy plane at the point A, comma, B. So I'm going to draw that picture for us to reference. To make things simple, I'm just going to draw a picture of a vector in quadrant 1. Okay, so A, B, here's our vector that terminates at the point A, comma, B, would have a magnitude equal to that, or this would represent the magnitude, right? The length would represent the magnitude of the vector u that we've drawn. We would have the direction angle theta, okay? So knowing that cosine, so if we think in think SOHCAHTOA, right? In this picture, where we have a right triangle, right, where this would be A, B, cosine would be equal to the side adjacent over the hypotenuse, which would be A over the magnitude of U. Sine, opposite over hypotenuse, would be B, value of B over the magnitude of U. So since A is the horizontal component and B is the vertical component, A will then, if we think about multiplying by the magnitude on each side, be equal to the magnitude of the vector times cosine of theta, and B would be equal to the magnitude of the vector times sine of theta. This is helpful for if you know the magnitude and the direction of the vector, but you don't know the horizontal or vertical component. So this is helpful for coming up with the vector, the representation of the vector in standard position. So the pointy brackets A comma B, if you know the magnitude and the direction angle. So this statement is true. So that means that if we want to find a vector that has a magnitude of 3 and a direction angle of 75 degrees, we can write that vector as 3 times cosine of 75 degrees, comma, 3 times sine of 75 degrees. Now, 75 degrees is not in the unit circle, so we can't simplify this any further. But if I give you an example of an angle that would be on the unit circle, like a vector V that has a magnitude of, let's say, 7, and then a direction angle of 150 degrees. That means that vector V, we can find the position vector, the horizontal and vertical components, by doing 7 times cosine of 150 degrees, comma, 7 times sine of 150 degrees. And we can simplify that further. Cosine of 150 degrees would be negative root 3 over 2. Sine of 150 degrees would be positive 1/2. So those would simplify to be negative 7 root 3 over 2, comma, 7/2. Okay, unit vectors. So any vector that has a magnitude equal to 1 is a unit vector. And you can find a vector's unit vector by multiplying the vector by 1 over its magnitude. So this would represent a scalar, right? Because the magnitude is a scalar. So you can think about dividing each component of the vector by the magnitude, or multiplying each component by 1 over the magnitude. So by the reciprocal of the magnitude, to find the horizontal and vertical components of the unit vector. Any vector is unit vector. So any vector that points in a certain direction, you can find the horizontal component and vertical components of its unit vector. So the vector that points in the same direction but has a magnitude of 1. Using our new way of finding the horizontal and vertical components, another statement could be for the unit vector would be 1 over the magnitude times the magnitude of V times cosine theta, comma, magnitude of V sine theta. Right, so really it just ends up being cosine theta, comma, sine theta. So if we want to find the unit vector that points in the same direction as the vector 5, comma, negative 2, we could first find the magnitude of the vector. So taking the square root of 5 squared plus negative 12 squared would be equal to positive 13. So the unit vector, which I'm going to call vector u, would be 1 over 13 times vector v, which, thinking distributive property, would be equal to 5/13, comma, negative 12/13. So that would be the vector in standard position that is a unit vector and points in the same direction as the vector 5, comma, negative 12. Now, vectors in terms of I and j. So another common way besides using the pointy brackets is to represent vectors in terms of I and j. And that's referencing two unit vectors. So the vector I is a common unit vector, which would terminate at the point 1, 0, and the vector j would terminate at the point 0, 1. So to draw the picture of each of those vectors, okay, so vector I, this is 1 and this is 1. This would be vector I. And this would be vector j. Okay, so they are called standard unit vectors or unit component vectors. So a vector u that has horizontal and vertical components a, comma, b can be equivalently expressed as a linear combination in terms of I and j. So as ai plus bj. So to show you this, why this works, all right, if we think about starting with the vector a, comma, b, that can also be written as the sum of two vectors. So how about the vector a, comma, 0 plus 0, comma, b, which if we thought about pulling a out, the scalar a out, that would be 1, comma, 0, a times the vector 1, comma, 0, and pulling the scalar b out, and 1, comma, 0 is vector I, and 0, comma, 1 is vector j. So it's just another way to represent vectors that are in standard position. Okay, so let's answer these two questions. So we can write vector u in terms of I and j. So vector u can also just be written as negative 5i plus 6j. Okay, and then we can also write vector, the new vector that's created for multiplying vector u by 4 and then subtracting vector v, which is being multiplied by 3. We can do that in terms of I and j. So 4u minus 3v, well, we can think about u as being written as negative 5i plus 6j minus 3 times vector v, which is 3i minus 2j, So then it's just thinking about distributing the 4 and distributing the 3 and combining like terms. So negative 20I plus 24J minus 9I plus 6J, and then we can just combine like terms. It makes it more algebra friendly. So that would be negative 29I plus 30J. And that would be equal, so in component form, right, it would be negative 29 comma 30. Okay, so I'm going to stop this video here, and I'm going to make a second video to talk about resultant applications of resultant vectors.